the end of this conversion problem. Okay, next problem says, what would happen to the position of the equilibrium when the following changes are made to the reaction below? Position of equilibrium. We're changing things on a system in equilibrium. Guess what kind of problem this is? Le Chatelier's principle. Okay, so this is the equation we have. Let's look at scenario A. Mercury oxide, HGO, is added to the system. Mercury oxide is a reactant, so what we're doing here is we are increasing the concentration of a reactant. And Le Chatelier's principle, if you literally go back and read the slide on Le Chatelier's principle about what happens when you change concentrations, when you increase concentration of a reactant, the equilibrium shifts to the left, or sorry, here to the right, towards products. So it will shift, you can say, towards products, or you can say shift right. Okay. Scenario B, what happens? Well, let me erase first. Done with A. Scenario B, the pressure on the system increases. Remember, when you're predicting shifts in equilibrium based on pressure changes, you need to consider how many moles of gas do you have on each side of the reaction. On the reactant side, we have 0 moles of gas. We have 2 moles of solid, no moles of gas. On the product side, we have 1 mole of gas. So as long as there's a difference in the number of moles, we can make the prediction about how it will shift. If you have the same number of moles, like 1 mole on each side or 0 moles on each side, then you can't predict. It wouldn't shift either way. But because we have fewer moles on the reactant side, more moles of gas on the product side, if the pressure increases, Le Chatelier's principle says that the system or equilibrium will shift to the side of the reaction with fewer moles of gas. I'm going to say that again. Equilibrium, if we increase pressure, equilibrium will shift to the side of the reaction with fewer moles of gas, which in this case is towards reactant. So it will shift left, or you could write shift towards products. What am I writing? Reactants. Shift towards reactants. Okay. So that's some more practice with Le Chatelier's principle. Next problem, the reaction of carbon monoxide with oxygen produces carbon dioxide, right? We already did this one. We did this. I'm pretty sure we did this. I'm going to skip it. I remember doing that one. It's in a previous video. Okay. Is this it? Last problem. We have reached the end. Okay, calculating osmolarity. So we have 3 different solutions here. Let's calculate the osmolarity of these solutions. Remember that osmolarity equals number of moles of particles per liter. So let's look at our first solution. We have 0.2 molar CaHPO4 calcium, and I actually don't remember the name of this anion. I would have to look at a periodic table, or not a periodic table, a polyatomic anion, or a polyatomic ion chart. But we have, this is number 5, 0.2 molar CaHPO4. So remember, when you're doing osmolarity, you have to ask yourself, do I have a compound on my hands that is ionic and it will dissolve into ions, or is it covalent? And we are dealing with, it will not dissolve into ions. And the molecule itself is the smallest particle we'll get. And I'm realizing I need to write smaller because we have 3 problems to do here. So let me zoom in. Number 5. If I have 0.2 molar CaHPO4, if one molecule of calcium, and then whatever the name of this anion is, dissolves, what would I get? I would get 1 calcium cation. Move this up. And I would get 1 HPO4 with a -2 charge anion. Okay. Guys, on the exam, you really aren't going to have to worry with me giving you ions like this that you don't recognize. You may not be able to identify or predict that that is a polyatomic ion. So I'll definitely give you osmolarity, but it would be with ions, cations, and anions that I've asked you to memorize from week 1 of class. Okay? All right. But knowing this, so let's write this out. 0.2 molar is just 0.2 moles of our substance per liter. And if I have 0.2 moles per liter of my entire substance, then I have 0.2 moles of calcium cations per liter plus 0.2 moles of my anion per liter. And these are the particles. When something dissolves into ions, this is the particles. So now to calculate osmolarity, we're going to add up the number of moles of particles. 0.2 moles of that particle, calcium, our cation, and 0.2 moles of our anion particle. Total gives us 0.4 moles of particles per liter. And that is 0.4 osmoles. So that's the first one. Number 6. If we look at number 6, we have 0.1 molar glucose, 0.2 molar sodium bicarbonate. Pause for a drink of water. So we're going to have a few things to add up here. Remember that a molecule like glucose, a molecule like fructose, a molecule like sucrose, those are the particles. They're not going to dissolve into ions. So if I have 0.1 mole, or 0.1 molar glucose, I have 0.1 mole capital G glucose per liter. And glucose here is my particle. I also have sodium bicarbonate. So if I have 0.2 molar sodium bicarbonate, I have 0.2 moles of sodium cations per liter, plus I have 0.2 moles of bicarb, HCO3. You guys should recognize this anion. That is one you had to memorize. So if you're rusty on your polyatomics, make sure you go review, or that will be difficult for you solving for osmolarity. So these are all the possible particles we would get in the solution. So we're going to add up the number of moles of particles, and you should get 0.1 plus 0.2 plus 0.2 is 0.5 moles of particles per liter, and that is 0.5 osmoles. So that's number 2. Okay. Lastly, or number 2, that's number 6. Number 7, we have 0.3 molar fructose. Down here, I'm going to write 0.3 moles of capital F fructose per liter. And fructose will not dissolve into ions. So it is the particle. Plus I have 0.2 molar magnesium chloride. So in that case, this is an ionic compound. It will dissolve. What will it dissolve into? It will dissolve, if I have one magnesium chloride molecule, I would get one magnesium 2 plus cation, but I would get 2 chloride anions because I have a 2 as a subscript there. So we're going to have to take that into account when we actually add up the number of moles particles. So if I have 0.2 molar magnesium chloride, then I have 0.2 moles of Mg2 plus cations per liter. But I've got to multiply that number by 2 here, because for every one molecule I'll get 2 anions. So 2 times 0.2 is 0. I would get 0.4 moles of Cl minus anions, which is another kind of particle, per liter. So 7 is a bit tricky here. Now we have everything written out though, we can add it all up. So 0.3 moles of fructose particles plus 0.2 moles of magnesium particles plus 0.4 moles of chloride particles gives us a total of 0.9 moles of particles per liter. That equals 0.9 osmoles. Okay, I think that does it. That has reached the end of our review. So if you made it all the way to this point, you are a trooper. Congrats, good job. I hope it prepares you or helps prepare you for